So, today we're going to be looking at advanced rational functions. So yesterday we basically just looked at what was going to happen if we shifted a rational function up, down, left, right, flipped it over the x-axis, stretched it out some. We looked at those different transformations. We did look at one that was a little bit different because we did look at the one where we had 1 over x squared, right, where we squared that denominator. So I would put that sort of in the advanced category. So this first one we're going to look at, I wouldn't consider in this like advanced category. But today we're going to look at ones that might have variables in the numerator and denominator that might look several different ways. So we're going to see what we can tell about the function just by looking at the equation. So what we're looking at today is going to be something that you are welcome on your homework to look at Desmos to check your work. But when you see these problems, they're going to be on a calculator inactive section of a test. So, so this will be stuff that you would be expected to be able to know without using the calculator. So, first we're going to talk a little bit about continuity. A function is going to be discontinuous if you cannot trace the graph without picking up your pencil. Okay, so if I look at this graph right here, if I try to trace this graph, I'm going to trace this side, it's looking good, but there's no way I can get to the other side of the graph without picking up my pencil and going up here, right, or over here, wherever you want to go. So, so if you have to pick up your pencil as you are tracing the graph, then that is not continuous, right? We kind of have an idea of that. It kind of makes sense. One type of discontinuity we're specifically going to talk about is a vertical asymptote. We've talked about those some already because we saw them with natural logs. They always had those vertical asymptotes that we looked at. But we're going to specifically be looking at them with rational functions this time. So for a vertical asymptote, the y-coordinate is going to go to infinity or negative infinity as x approaches a given value. So if I put a, and this is true for all, not just rationals, but if I put me a dotted line here where my vertical asymptote is, what this means is as I trace this graph, as I get closer and closer and closer to a value, and for this one that value is -2. As I get closer and closer and closer to -2, my y values just plummet, right? They go to negative infinity. From the other side, as I get closer and closer and closer to -2, they keep going up and up and up and up. So we're seeing that sort of, the graph sort of like veers off as it gets closer to that point. These can go both in the same direction. They can both go up. They can both go down. They can go opposite directions, or they can just approach from one side like we saw with those natural logs, right? Because the log equations, they did not have the second half of the graph over here. But with rationals, they're going to look, for basic ones, they're going to look like this. And so for this particular problem, we would have a vertical asymptote at x equals -2. Now this one I've got the graph sitting there, so you can tell what the graph is going to look like because I've graphed it for you. But how would I know this if I was not looking at the graph? What about that equation could possibly tell me I've got an issue at -2? What? The +2 right here. What's going to happen if I plug in -2? I get a 0 in that denominator. And what is 1 over 0? What do we call it? Undefined. Okay, so what we're going to see with these is that a 0 in the denominator that is not canceled out is going to cause a vertical asymptote. So we should be able to tell where vertical asymptotes are going to be even if we don't have a graph, right? So that's what we're looking at today. We definitely should be able to find it from a graph. We also want to be able to find it even if we don't have a graph. So if I look at example 1, I only care about what is in the denominator. If it is equal to 0, I'm going to get a vertical asymptote at that point. So I'm going to have x plus 7. If it equals 0, that's going to give me a vertical asymptote. To solve that, I just subtract the 7. So x equals -7. That would be my vertical asymptote for this graph. With the simple ones, you can also think about shifting the graph. What does that plus 7 do to the graph of the 1 over x? Left 7, right? So normally the y-axis would be our vertical asymptote. This is going to move it to the left 7. So that would be x equals -7, which is where your vertical asymptote would end up at. Now, a problem like number 2, we can't really think about the shifting up, down, left, or right for this because it's a more complicated function, right? We're not starting with 1 over x here. But the same thing is still true. Our denominator right here, if it equals 0, then we have a vertical asymptote unless we're going to see, unless that 0 cancels with the numerator. I'll talk about that more here in a minute. So we're going to say x squared minus 3x plus 2. That is going to equal 0. To solve this, I have several options. I could complete the square. I could use quadratic formula. But the fastest, if it will factor, is to factor. Right? So if I factor this, I get x minus 2 and x minus 1. And then I would just set each one equal to 0. So x minus 2 would equal 0, which would give me x equals 2. And x minus 1 would equal 0, which would give me x equals 1. Okay. These are both going to be vertical asymptotes. We'll talk a little bit more about holes here in a second. So we'll have vertical asymptotes at both places. Okay. When you work on this for your homework, you are welcome to go over here to Desmos, type this stuff in. You're welcome to do this. If I type in x equals 2 and x equals 1, so if I do this, you can see those look like vertical asymptotes on your graph. So you're welcome to check your work that way, but just know whenever you see these problems, they're going to be on calculator inactive. So you're not going to be able to do that on the test or quiz for this. How did I do the quiz on this one? I have to look at the quiz in a second to see what I did on that. I'm pretty sure the quiz is not calculator active for these. I'm almost certain of that. But I'll double check here in a second because our quiz will be tomorrow. Alright, so a point discontinuity. Okay? A point discontinuity is going to happen when there is a hole in the graph, but the pieces of the graph match up. And so there are 3 different terms that are all interchangeable for this type of discontinuity. And obviously one of them is a point discontinuity. The other is a hole. I'm probably going to call it a hole more than anything because I like that term the best. And the other that you're going to see that we're going to write in this parentheses is removable discontinuity. So here's what happens with a point discontinuity or a hole in the graph. I've got this function x plus 5 over x plus 5. So I'm going to make myself a chart. I'm going to plug in some numbers. So if I plug in 0, right, I'm doing 0 plus 5 over 0 plus 5. That is going to give me 5 over 5, which is just 1, right? If I plug in, so that means I could graph the point 0, 1. That'd be right here. I could graph 4, right? 4 plus 5 over 4 plus 5. 9 over 9 also equals 1. So I got the point 4, 1. Let's graph a negative. Let's do a negative number, negative 3. 4 plus negative 3 over 4 plus negative 3. It's 1 over 1. 1. Oh, I'm sorry. I don't know what I'm doing. I'm looking at the problem for. Let's do negative 3 plus 5 over negative 3 plus 5, which is 2 over 2, which does still equal 1. That'll look better, Troy. Okay, so we can just plug in. What if I plug in 7? What am I going to get? 1. Right, so if I graph all these points, it is looking like this is just a horizontal line, right? Except there is one number I can plug in that's not going to give me 1. What is that number? Negative 5. If I plug in negative 5, I have negative 5 plus 5 over negative 5 plus 5, which gives me 0, 0 over 0. 0 over 0 does not equal 1. Okay, it is what we call the indeterminate form, and it's a little bit different than undefined, but for our purposes here, we can kind of think of it as undefined. So what happens on this graph is you can't plug in negative 5. You can plug in any other number in the world, you're going to get 1. You can pick any number that you would like, you're going to get 1 every time. You can plug in pi, and you would get 1. You could plug in e, and you would get 1. You could plug in 7,523, you would still get 1. But if we plug in negative 5, we don't get anything, right? It's undefined. So what's going to happen, the way that we would graph that if we were graphing it, is we would put an open circle right there at the point negative 5, 1. And so the graph is going to look like this. So the graph is mostly continuous. It looks like it's going to be continuous. But at that single point, it's not continuous. You have a hole in the graph. This is called a point discontinuity a lot of times because it just has this single little dot that's missing out of the line. It is also sometimes called a removable discontinuity because you could remove this discontinuity if you just put one point there, right? With the vertical asymptote, that's not the case. We got to do like major things. We got to somehow like move these and connect them or something, right? But this we could fix if we just had one little point we could place right there in the spot where it's missing. So that is why it is sometimes called a removable discontinuity. You want to make sure that you know all three of these terms and know that they are interchangeable. They're no different from each other because I may use any of the three whenever I'm asking questions. I might ask for a point discontinuity on one problem, and then I might ask about a removable discontinuity or a hole on a different problem. And I do that because stuff you're going to run into, things you're going to see wherever, all those three terms are used in a lot of different places, depending on what worksheet we're doing or what book it comes from or what test it's on. They may use any of them. So in calculus, AP calculus, the term they like to use is removable discontinuity. That's the one they use the most, but all three could be used. So, also, I do want to show you this on Desmos because Desmos is a little bit deceiving here for this one. F of x equals x plus 3, x plus 5 over x plus 5. If I graph this, it just looks like a straight line. I don't see a hole, right? But if I go over here and try to get my cursor to be right there perfectly on 5, oh, it did it, but I moved it. -5. If you can get perfectly right there at -5, there is a hole. It's just that what's happening is like points don't really have width, right? So at -5.00000001, this still equals 1, right? So points don't really have width. So if I'm trying to graph this, it's not going to show up. If I graph by hand, I usually put an open circle there to indicate that's what's happening. But Desmos does not do that unless you put the cursor on the line. So you can't see holes whenever you graph them on Desmos unless you actually trace that part of the graph. So let's continue. What causes a hole? Okay, a hole is caused by a 0 in the denominator that cancels out with a factor in the numerator. So like that problem we just looked at was x plus 5 over x plus 5. Those two factors would cancel each other out, right? Because everywhere except for -5, they're equal to each other and are just going to cancel each other out and become 1. Okay, so most of the problems you're going to see are going to look something like this. Find any discontinuities and describe them. So it's important to remember discontinuities only come from the denominator. It is okay to have a 0 in the numerator. So when I'm doing a problem like this, the first thing I'm going to do is, if I see something squared, is I'm going to try to factor it. So I've got x squared plus 2x minus 15. And I'm going to factor that. I'll have an x here and an x here. I got -15, so that's going to be a +5 and a -3 for that. And if your factoring is a little weak, now would be a great time to brush up on that because you will need it a lot. Several things we do in this class. So, the discontinuities come from the denominator. So I'm looking at the denominator before I look at anything else. Okay, this is where I'm looking at. And I know that x plus 5, if x plus 5 equals 0, which is when x equals -5, that is a discontinuity. I also know that if x minus 3 equals 0, which is when x equals 3, that is a discontinuity. These are both discontinuities. Okay? The question is, what type of discontinuity? So, does x plus 5, does it cancel with anything in the numerator? It would not, right? So, this one is going to be a vertical asymptote. However, this factor that I used right here to get x equals 3, does it cancel with anything in the numerator? I have this same factor up here. It does cancel. So, since that cancels, this would be a hole in the graph, or a removable discontinuity, or a point discontinuity, whichever term the worksheet's asking you to use there. So if your term cancels, it gives you a hole. If it is just there in the denominator but does not cancel, it gives you a vertical asymptote. Okay, questions? All right, let's try the next one then. Smith, how would I factor that numerator? Okay, what do you got on the bottom? You can give me the bottom. Very good. X plus 3. X minus 3. Good. We also need to factor the top just to see if anything will cancel. So what do you think on the top there, Smith? Okay. negative 3, negative 3. Remember, you're wanting it to multiply to give you the last number, which is 9. They got add or subtract to give you the middle number. So if you have negative 3, that'll give you 6. If you multiply them together, it'll give you 9. Okay, now, the discontinuities only come from the denominator. Okay, the numerator is there to help us see if they cancel, whether it's a whole or vertical asymptote. But we have discontinuities at these two places, so x plus 3 would equal 0 whenever x equals negative 3, right? And x minus 3 would equal 0 whenever x equals positive 3. So if I'm looking for the one that cancels, it's this x minus 3. Right? It will cancel. I will have x equals 3 right here. Is the one that I got from the x minus 3. So this is a hole in the graph, or a point discontinuity, or a removable discontinuity. Does x plus 3 cancel? It does not. It can't cancel with this. It's really close, but there's a plus here and a minus here. Those do not cancel. So, so this is going to be a vertical asymptote. You do not do anything with this extra factor on the top. Discontinuities don't come from the top. The only reason we even care about the top is just to see whether it cancels, right? That's the only reason we even factor it. If it only asked for discontinuities, we wouldn't even have to worry about the numerator at all. But if it wants to know if they're holes or vertical asymptotes, we have to think about it. Okay, questions? Okay, same instructions here. Our discontinuities only come from the denominator because we can't have zeros in the denominator of a fraction. So if x minus 5 equals 0, that means x equals 5 is where we're going to have that discontinuity. And does x minus 5 cancel with the numerator here? It does not. So this is just going to be a vertical asymptote here. We don't do anything with the numerator because it's okay to have zeros in the numerator, right? So the only reason that we even think about it is to see if it cancels with the denominator. All right, factor that next one for me. It's got a 2 in front of that x squared. It's going to make it a little tougher on factoring. I'll give you a second there. Okay. Check with your neighbor, see if they've got it factored. See if you guys factored the denominator the same. Okay. Who can tell me how this one factors? Anybody got it? Somebody's got it, surely. Everybody's afraid. Anybody got it? Want to give it a try? Doesn't sound like anybody else has got it, so there's no need to be worried. I'm not going to call because you guys looked a little unsure whenever you were discussing. You should get a 2x and an x. You should have a plus 1 right here and minus 4 right here. Anybody have it factored correctly? I'm pretty sure. Let me make sure I've done it right. Yeah. Do we not know how to factor with a number in front? So, whenever you're factoring with a number in front, you got 2x squared minus 7x minus 4. So, these first terms right here have to multiply to give you 2x squared. Right? Normally, we don't have to think about that so much because it's just an x and an x that gives us x squared. But when we have a number in front of it, it makes a difference. So the only thing you can really do for 2x squared is a 2x times an x. Right? So I put a 2x here and an x right here. For the last term, you've got negative 4. So your numbers have to multiply to give you a negative 4. You got some options for this. You got negative 1 and 4, negative 2 and 2, or we could switch the negatives on those, right? But I'm not going to list those separately. So you can't tell right away. Like the other ones, you can tell, oh, I've got negative 2 and negative 3 and negative 5 in the middle, so that's going to be it. The other ones you can tell without really having to guess and check. You have to guess and check on these. So you're just going to pick one. Like let's say you try negative 2 and positive 2 first. And then you just multiply it back to see if it works. When you get really good, you can do this in your head, and you don't have to like guess and check quite as much. But if you're not good at it yet, you're going to have to guess and check. So you'll get 2x squared plus 4x minus 2x minus 4. So this gives me 2x squared plus 2x minus 4. That does not match this, so that was wrong. All right, so now you got to back up and try again. So the 2 and negative 2 did not work. Sometimes it will work to switch where they're at, but in this particular case, because they're both 2's, switching's not going to help any there. So if I try then 4 and 1, so minus 4 plus 1. This isn't right either because I told you what the answer is. But if I test this, now the first term should work every time. You're getting 2x squared, right? This is going to give you positive 2x. This will give you negative 4x. I could probably quit now, right? You should see that's going to give me negative 2 also. That does not work. So then it may be helpful to switch the 4 and the 1. So 1 and 4 right here. So here, now I've got 2x times x, which is 2x squared. I've got positive 8x. Right here I'll get negative 1x, and I get minus 4. Is this one right? No, but we're getting really close now, right? Because that is 2x squared plus 7x minus 4. We got the right number, just not the right sign. All right, so what could I do to make the sign switch on this? If this 8 right here was positive and the 1 was negative, I'm sorry, the 8 was negative and the 1 was positive, it would work. So if I switch right here, my positives and negatives, so I've got plus right here and a minus right here, then I get 2x squared, I get minus 8 plus 1, that's going to be a negative 7 right there, which is what I want, so that is factored correctly. So it can be kind of a pain when you have a number in front of that x squared, but you just have to guess and check. Whenever you've done it many times, you might, like, I can look at this, what I'm doing in my head is I'm going, oh, that needs to be, what will I get here? Oh, that'll be negative 8, that'll be positive 1, that'll work. So I can do it in my head, but if you don't have a lot of experience with it yet, and it was kind of sounding like we might not have a great amount of experience with it, then just guess and check until you get it. So a short factoring review, I've got 2x plus 1 and x minus 4 in the denominator. That's where my discontinuities are going to come from. That 2x plus 1 is a little more complicated than the ones we had before, but you're just doing 2x plus 1 equals 0. So you would subtract 1. So 2x would equal negative 1. And you would divide by 2. So x would equal negative 1/2 for that. And then over here, we'd have x minus 4 equals 0, which will just give us x equals 4. Okay. Do either one of those cancel with the numerator? They do not. That 4 almost does, like it's close, but it does not. So since you don't have anything cancel with the numerator, both of these would be vertical asymptotes. You don't do anything with the numerator. There's no other discontinuities from the numerator. It's only from the denominator. Okay, questions there? All right. Okay. We're going to look at just a few more ways that these questions can be asked. Okay. So we're really not doing anything new. It's just a few more ways the questions might be asked. So this seems obvious and like it does not need to be stated, but if a function is not discontinuous, then it is continuous. So if a function does not have any discontinuities, it would be continuous. So one way that you're going to see questions like this asked is they're going to say, is the function continuous on the given interval? Okay, so here for number 7, I've got f of x equals 3x minus 7, and we're looking at the interval from negative 2 to 3. Okay. Do I even have a denominator for this equation? I do not. Am I going to have zeros in the denominator if I don't have a denominator? I will not, right? This is just a line. It is continuous everywhere. So you may see this thrown in there to try to confuse you, something that doesn't even have a denominator, something like a quadratic or a linear equation or a cubic equation or something. Those are just always continuous if they don't have that denominator. So this is linear. It's always continuous. It doesn't even matter what the interval they gave you was. This is going to be a yes. You are always continuous on that interval. Okay. For 8, we've got 1 over x plus 9. Okay. We need to find our discontinuity. This is going to have a discontinuity. It is going to come from the denominator. It is going to be wherever x plus 9 equals 0, so x equals negative 9. So we have a discontinuity there. If you want to be specific, it is a vertical asymptote, although this did not ask us for that, so we don't have to say that. But they're asking us if the function is continuous from 0 to 9. So is the function continuous from 0 to 9? This would be a yes. It is continuous from 0 to 9 because you have a discontinuity, but it's not between 0 and 9. It's outside of the window that you're looking at. Okay, questions on that? All right, example 9. Again, we're looking at the denominator. We're looking for a discontinuity. So where that denominator equals 0, we're going to have a discontinuity. So we would subtract 2. 3x equals negative 2 divided by 3. X is going to equal negative 2/3. What type of discontinuity is it? Are you sure? It's a whole. How do you know it's a whole, Maggie? It would cancel with the top. So this is a whole, but it really doesn't matter. A discontinuity for this is a discontinuity. It doesn't matter whether it's a whole or a vertical asymptote. It's still discontinuous there. So although I've just asked you that because I wanted to reinforce what we were already doing, it doesn't matter. whatever gives you a 0 in the denominator is a discontinuity. So we have a discontinuity, but is it on the interval they asked us about? It is not. So this would still be a yes. It's continuous on that interval. If they asked us from -1 to 1, then we would say no, because -2/3 falls in that interval. We good here? Okay. Another way they're going to ask this question, rather than saying, is this continuous on this interval, they're going to tell you to tell the intervals where it's continuous. Okay? So when you see these problems, again, you really only care about the denominator. Okay? The denominator is all that you care about. So you are looking for, you can factor that denominator if you want. This would be x plus 4, x minus 4, which means you've got discontinuities at when x plus 4 equals 0. So x equals -4, and when x minus 4 equals 0, which is when x equals +4. Your other option on that is you could have just done it this way, x squared minus 16 equals 0. You can move the 16 over and square root both sides, which will give you plus or minus 4 there. So either route will get you there. So you have discontinuities at -4 and 4. Notice I didn't factor the numerator because it really doesn't matter whether they're wholes or vertical asymptotes for this. If I needed to know that, I would need to factor the numerator, but it doesn't matter. So, so I have discontinuities at -4 and 4. So this function is going to be continuous everywhere except for those points. So what I'm going to do is I'm going to start at -infinity. I'll go up to the lowest number, which is -4. I'm going to use this U right here. That means the union of the two sets. So it's basically just like saying and here. Or is it or? I think it's or. And then so -4 up to 4, and then from 4 to infinity. I want to use parentheses with everything because if I use a bracket, it includes the -4, and I don't want to include it. Questions on that one? All right, we just got these couple more to think about. Here, that should be good. Okay. So for 11, again, we only care about the denominator. We are going to factor that. So x plus 3, x plus 1. And we're looking for where those equal 0. So x plus 3 equals 0 at -3. And x plus 1 equals 0 at -1. If they wanted us to tell wholes or asymptotes, we would have to factor the numerator, but it doesn't ask for that. So -3 and -1 are our discontinuities, so we would just say that this is continuous from -infinity up to -3, -3 to -1, and -1 to infinity. All right, and one more thing I'm going to throw in here is just a little bit of piecewise functions. We're actually going to do a whole section on piecewise functions later. But this is a piecewise function that tells us if I'm plugging a number less than 4, I'm going to use the top equation. If I'm plugging a number greater than 4, I use the bottom equation. I don't have denominators on either one of these, so absolute value of x plus 2 is continuous everywhere, and 4x minus 10 is continuous everywhere on its domain. What I need to know is, do these two pieces of the graph match up, right? Because The only issue I'm going to have is right here at 4. So, I can very easily answer that this is going to be a no, because if I want to plug in 4 to this, which equation should I use? I can't, right? Because I don't have a or equal to sign for either one of these, right? So if I'm trying to plug in 4, there's nowhere to plug it in. This equation only applies for less than 4, and this one only applies for greater than 4. There's nowhere to plug in one that is exactly 4. So as this problem stands, we would have a discontinuity at x equals 4. So we would say negative infinity to 4 and 4 to infinity. Let's pretend that I have the function that looks like this, absolute value of x plus 2. X is less than or equal to 4, and then 4x minus 10 for x is greater than 4. So if I'm pretending that I do in fact have or equal to right here, then if I plug in 4, I should use the top equation. I will get absolute value of 4 plus 2, which will give me 6 there. What I want to know, so like that's going to graph an absolute value. It's going to be, look something like this. We'll talk more about graphing these later. What I want to know is that going to meet up with where this one would end? Although I don't use 4 to plug it in, I could still see where that open circle would be. And so if I did 4 times 4 minus 10 here, that would give me 16 minus 10, which also gives me 6. So what happens there is you have like an open circle and a closed circle that fills it in. Those would meet right there. So if you had an or equal to sign right here, then you would be continuous everywhere from negative infinity to positive infinity. I just wanted to introduce that a little bit. We'll talk about piecewise a little bit more in depth later. Okay, questions on that?